All right, this is a video on using systems of linear equations to model and solve real-world scenarios. Okay, so applications of linear systems. And we're really not going to do any sort of an introduction. We're just going to go straight into solving an example. We'll do 3 different examples in this video. So the first one I want to show you involves a classic systems of equations problem that you might encounter in a business, and where you might want to try to find where your break-even point is, where your revenues reach your costs so that your profit becomes positive. Okay, and so the scenario here is a fashion designer is selling hats, and the material for each hat costs $5.50, and hats sell for $12.50 each, and $1,400 is spent on overhead. So we're curious. We're like, how many hats do we need to sell to break even to actually get into the black, out of the red, and actually make a profit? Okay, so let's just define some variables first. We can say X is the number of hats, because that's what we're being asked about, right? How many hats? So let's call that X. Looks like the other thing that varies or is unknown in this equation, or that can vary, is the dollar amount. Okay, so we're wondering how many dollars we'll be bringing in for each hat we sell, or spending for each hat that we make. Okay, so we can write a couple different equations. We can write a cost and a revenue equation. The cost equation is going to be 550x plus the $1,400 we need to get our business off the ground. And the revenue equation is just going to be, what are we bringing in? It's 1250x, 12.5 times x. Okay. So this is a classic example of being able to use the substitution method of solving systems of equations. What I just circled in red is equal to y, and so it's also equal to that y, right? So we can plug it in, we can substitute, and we'll have an equation with just x's in it. So let's do that. 12.5x is equal to now 5.5x plus 1,400. And we can, looks like we can subtract 5.5x from both sides. Okay, and that's going to eliminate the x's on the right. We'll have 7x remaining on the left side, equal to 1,400. That's a pretty easy final step. X is going to be 200. We'll divide both sides by 7. So then think about 200, what is it, $200, 200 what? Well, actually x was number of hats, okay? So that's why we were careful to define our variables. So we have to sell 200 hats to be able to break even. Let's think about if that makes sense. Each hat gives you a $7 profit, right? 550 to 1250 is a $7 profit. And so we're going to use those profits for each hat to spend down our $1,400 that we had to spend on overhead. Okay, so to sort of use up that debt. So that kind of makes sense. 200 hats we need to sell. Next one involves some curious results, and I got this problem out of a textbook, and the conclusion in the textbook was it's an impossible problem to solve, but I kind of disagree with that. I think that there actually is a real meaning to the solution, so I want to kind of take you through that. I thought it would be interesting to look at. So the zoo fills 2 water tanks for an exhibit. One tank has 50 gallons to start and is filled at a rate of 10 gallons an hour. The second tank has 29 gallons of water and will be filled at a rate of 3 gallons per hour. When will the tanks have the same amount of water? Okay, so let's define our variables, and we can have x represent time in hours, and we can have y represent water in gallons. Okay, so let's write a couple equations. So for the first tank, it's starting with 50 gallons, and we're adding 10 gallons per hour. Okay, so it's a classic slope-intercept form, 10x plus 50. For the second tank, we are only adding 3 gallons per water, and we are starting with 29 gallons. Maybe you can tell that the second tank will never catch up, right? It has less water to start, and it's being filled at a slower rate. So it's never going to catch up to the first tank, right? And I think that was the intent of the textbook in showing you that we're going to get an interesting result, but we'll still talk about what that result means. So Once again, substitution, okay? So 3x plus 29 equals 10x plus 50. We can, let's see, subtract 10x from both sides. And these 10x's cancel. We have a 7x plus 29 equals 50. Let's subtract 29 from both sides, accumulate all the numbers on the right side, all the x's on the left. And we get a 7x equals I think I made a mistake somewhere. Okay, I see my mistake. I'll explain it in a second. Hope you saw it. Hope you saw it. Did you find it? It's right here.
Okay.
Hope you saw it too. 3x minus 10x is not 7x. It is negative 7x. So I'm going to bring those negatives down. Okay? Remember, have a growth mindset. Mistakes are good. That's how we learn, right? And so let's keep going. Let's solve. Let's divide both sides by negative 7. And we get x is negative 3. Let me write that a little bit cleaner here. So x is negative 3 hours. So the textbook at this point said, let me see, so it is not possible to have time be negative 3 hours, so the tanks will never have the same amount of water. Well, I disagree. I think it is possible for time to be have negative 3 hours. We can think of that as what happened 3 hours in the past, 3 hours prior to the start. So maybe we would need to assume that the tanks had been being filled this whole time, right? So over the past few hours and including into the future, the tanks are being filled at these particular rates. And if that's the case, then 3 hours ago, the tanks had the same amount of water. And in fact, they would have had 20 gallons, I think. We could plug in 3 for either of these equations. And we can say y equals 10 times negative 3. Plug in negative 3. So y equals 20. Okay, so it's a curious solution, but it's a reasonable solution, I think. 3 hours ago, assuming the filling of the tanks had been continuing over that time. That's when the tanks had the same amount of water. And then this last one is another classic sort of systems equation that you'll come across a lot. It's a wind and current problem. Sometimes it'll be you're rowing upstream and then you return downstream, and you need to figure out, what the current speed is, what your speed in still water is. Here's a similar example, except you're flying through the air. Okay, so you fly west from North Carolina to Los Angeles, while simultaneously your friend flies in the opposite direction. The wind is blowing west to east. That's typically how the wind patterns are in the United States. Your ground speed is 495 miles per hour. So as you are flying from North Carolina to LA, the speed as you pass over the ground, the speed of you relative to the ground is 495, whereas your friend's ground speed is 550. So what's the speed of the wind? Your friend has a higher ground speed because your friend has a tailwind, right? And you have a headwind. Okay? So let's see here. We can define a couple variables. Let's have A be your airspeed. And what's interesting about this one is you don't know what the distances are, and you don't know what the times are. You just know what the speeds are. And let's have W be the wind speed. And I hope you can see that your ground speed is a combination of the airspeed and the wind speed. So for your friend, let's do that one first. The airspeed plus the wind speed is going to equal 550 miles per hour. Okay, and let's assume you're in the same sort of a jet, the same sort of a plane that has comparable airspeeds. Okay, for you, the airspeed minus the wind speed is 495. Okay, so the wind speed is decreasing, is being subtracted away from your airspeed to get you the ground speed of 495. This is a classic case of where we can use elimination. It's set up so nicely. You can see that these W's are going to cancel if we just add these two equations together. And so we will get a 2A is equal to 550 plus 495 is 1045. So we could divide then through by 2. And so we get A is equal to 522.5. So that's your airspeed. So through still air, or just your speed relative to the air that you're traveling through, is 522.5 miles per hour. Okay. We still need to find the wind speed. That's what was being asked. So we can take that value of A and plug it into either of our equations. I think it's a little bit easier to plug it into the first. So 522.5 plus our unknown wind speed is 550, and we can just then subtract the 522.5 from both sides. And let's see what we end up getting. So the wind speed is 27.5 miles per hour. Okay, blowing west to east from LA to North Carolina. Nice, we made it. That's a good place to stop right there.